Alright everybody, welcome back. In this video we're going to talk about information related to section 6.2 of AP Calculus, approximating areas with Riemann sums. This is part 1 of my lesson. There will be a second part. It's possible that both parts might be in multiple videos as well. So here we go. A lot of text to start off with today explaining the idea of what a definite integral is and what a Riemann sum is, as well as what the trapezoidal rule is. So if you take a look at this, we're going to introduce the mathematical notation for the definite integral, which is what you see right here. And the way we say this is the integral from a to b of f of x dx. Okay, there are some other ways that we can say that, but that's typically how I say it, the integral from a to b of f of x dx. So what I want you to think about right now is I want you to think about this particular expression here represents the area of a region between the curve f of x and the x-axis, where x equals a is the left boundary and x equals b is the right boundary. And this goes right back to section 6.1, where we accumulated things by finding the area between the curve and the x-axis. Just like in the last lesson, if we have the curve above the x-axis, that area is counted as positive towards this value. And when we have the curve below the x-axis, that area is going to count negative towards this value. Okay? Now, in our last lesson, it was really easy for us to find these areas because they were all regions that were made up of, common shapes, rectangles, triangles, semicircles, etc., etc., that we could find using stuff from geometry. But starting today, we're going to look at curves where that's not necessarily the case. So, consider the following situation. Suppose I have a curve defined by the function y equals negative 1/5 x squared plus 2x plus 3, and I want to find the area of the region below that curve, above the x-axis, and between x equals 2 and x equals 10. And this is a strictly positive curve. So, what we're looking for is this area right here that I've kind of colored in. Didn't do a great job of coloring it in, but we're looking for that area. Now the thing is, we don't have any formulas like we do for a rectangle or a triangle or a semicircle or anything that will enable us to find this. So instead, what we're going to do for right now is we're going to try to approximate the value of this area. And we're going to use two primary techniques possibly to approximate. Now, I would choose one of these in a given situation. I might use what are known as Riemann sums. So what's going on with a Riemann sum is we're going to approximate the area using some number of rectangles. And we're going to use a consistent method for determining the heights of those rectangles. The most common Riemann sums that we're going to use in this course are the Left-Endpoint Riemann sum, the Right-Endpoint Riemann sum, and a Midpoint Riemann sum, where we're subdividing this region into a number of rectangles. And then, depending on which of those we're using, that dictates how we determine the height of the rectangle that we're using. And you'll see this a little bit better when we talk about actually doing this for this curve. Another method that we can use for approximating this area is using what's known as the trapezoidal rule. That'll be just like using a Riemann sum, except instead of using rectangles under the curve, we're going to put trapezoids under the curve. And so that'll impact our calculation a little bit, but it's just another different method for approximating the value of this definite integral. All right. Let's go ahead and do this. Example 1, we're going to look at part A, and my word choice is poor here. It's probably not that we're really approximating is a better word choice. We're approximating the integral from 2 to 10 of negative 1/5 x squared plus 2x plus 3 dx, and we'll go through how we do that using all of these methods. First, we're going to start by using a left Riemann sum with 4 subintervals. Okay, so 4 subintervals tell me how many rectangles we're going to divide this into. And since we're going from 2 to 10, that means the width of my rectangle is going to be the upper endpoint minus the lower endpoint divided by the number of subintervals. And so each of our rectangles here is going to be 2 units wide. And so I'm just going to go ahead and mark off my horizontal axis 2 units apart. Then, since we're using a left Riemann sum, for the interval from 2 to 4, the height of the rectangle is going to be the value of the function at the left endpoint. So right here, that's going to be the height of my first rectangle. I'm just going to freehand these. And then for the next interval from 4 to 6, the height of my rectangle is going to be determined by the value of the function at the left endpoint. I'm going to go up here. And there's my rectangle that I'm going to use to approximate the area there. Then for my next interval from 6 to 8, I'm going to use the function value at 6. It's the height of my rectangle. And then for the next interval from 8 to 10, I'm going to use the value of the function at 8. Okay, so now I need to calculate the area of each of these rectangles. And add those together, and that'll give me my left Riemann sum for 4 subintervals. So the first rectangle is 2 units wide, and the height of it is going to be f of 2. And the second rectangle is 2 units wide, and the height of that is going to be f of 4. And the third rectangle is 2 units wide, and the height of that's going to be f of 6. And the fourth rectangle is 2 units wide, and the height is going to be f of 8. And so what I can do is I can factor the 2 out of all of this here, since I have uniform width rectangles. And then I just need the values of the function for these different x values. One of the easiest ways I can do this is I can go ahead and type this function into my y equals screen and set up my table to ask me for my independent, and then go to my table and just type in the values that I want the function at. I want it at 2. Come on, did I not? No, I didn't. Change that to ask. And then when I go to my table, I can type these values in: 2, 4, 6, 8, and it gives me all those function values: 6.2, 7.8, 7.8, and 6.2. And then I go ahead and finish my calculation. That's looks like 28 when I add all those together. And there's my approximation. My left Riemann sum approximation for the value of this integral is 56. All right, let's go ahead and do the same thing. Right Riemann sum with 4 subintervals. Again, we're going from 2 to 10, 4 subintervals. So each one of those subintervals is going to be 2 units wide. It's going to divide the area under this curve into 4 regions. Only now, with a right Riemann sum, we're going to use the value of the function at the right endpoint of the interval to determine its height. So right endpoint, right endpoint, right endpoint, right endpoint. So this approximation is going to be 2 times, and then the first rectangle, the height is f of 4. Second rectangle, it's f of 6. Third rectangle, it's f of 8. Fourth rectangle, it's f of 10. Already found f of 4, 6, and 8 in the last problem. And then I just need f of 10. I'll go ahead and type 10 in here. And that value is 3. Now we add all those together. That's 15.6, 21.8, 24.8. And we multiply by 2. And my right Riemann sum approximation is going to be 49.6. Okay? All right, let's go ahead and we'll do the midpoint Riemann sum. Same thing, 4 subintervals. So we're going to break it down into those same 4 subintervals. And now, since we're using a midpoint Riemann sum, we want the value of the function at the midpoint of each of the intervals. So the first rectangle is going to be from f of 3. And the second one, the height of the rectangle, is going to be f of 5. And the third rectangle, wow, my hand got a little wavy there. It's going to be f of 7. And then the fourth rectangle, that height is going to be f of 9. And so now I'm going to go back and I'm going to calculate all those values. So I need 3, 5, 7, 9. And I get 7.2, 8, 7.2, and 4.8. So that's 15.2, 22.4, 27.2. And we end up with the approximation being 54.4. All right. I think I'm going to call it quits there. I don't feel like I have sufficient time to do part D of this example, which is showing you how to use the trapezoidal sum and set that up with 4 subintervals. So we'll come back in the next video and we'll do that, and we'll talk about whether these approximations are underestimates and overestimates a little bit, and some of the indicators that we can use to figure that out in our next video. So we'll see you then. Have a great rest of your day.